started here. This is chapter 2. We're going to talk about atoms again. We're going to do the notion of isotopes. I'm going to talk about the periodic table, regions of the periodic table, where it comes from. But before we do any of that, let's review a little bit of what we did in lab on Tuesday. On Tuesday, the first task that we had was to read a meniscus, so read a volume. This is a section of a 10 mil graduated cylinder, and this is the water meniscus. Like I said, when you read a meniscus, and with water anyway, you're going to be reading the very bottom of our line here. Now, this starts at 6, and every little line in between is 0.2 milliliters. So we would read this. We would say it's 6, 6.2, 6.4, 6.6, and then just a little bit. So we're guessing what the last little bit is. So the proper number of significant figures here would be 6.6, and then a guess. I would guess that's about 6.62. So 3 significant figures from that reading. 6 we're sure of, 0.6 we're sure of, and 0.2 we're guessing. This is our larger. It's actually a 100, but that'll work. Here's our 50 line. Again, here's our meniscus right here. We read right at the bottom. Each division here now is 1 milliliter. So we're at 50, 51, 52. We're sure of 52. And now we're going to guess our last one. It's almost up to the 53 mark, but not quite. You know, mentally dividing us up, about 52.8 would be a decent guess. Now, a water meniscus will always be negative like this. Quite often you're going to work with, in other courses, not this one, with something like mercury. Mercury has a positive meniscus, so instead of going down like water, it goes up. With a mercury meniscus, you always read the top, so it would be right there. Any questions on that?
Is it because mercury is much more dense than water, it has the positive meniscus instead of the negative?
Water has a negative meniscus because the glass basically has a negative charge, and the water molecules can hydrogen bond with it. And when they do, they tend to climb up the sides. Mercury doesn't do anything, doesn't interact at all. So it tries to form a sphere, if you will. That's the minimum surface area it can show. So that's the difference between the two. We also did a bunch of measurements on the balance, and we did some calculations and stuff, and there were questions about rounding. So let's just do a couple quick exercises in rounding. We are going to round 5.379 to 3 significant figures. So we're rounding here to 3 digits. So what we're going to have to do is get rid of this 9. The basic rules are very simple. The digit that you're getting rid of, if it's more than 5, we up it by 1. Up the preceding by 1. If it's less than 5, we drop the preceding or it's unchanged. So our digit that we're getting rid of here is a 9. That's more than 5. That means the one in front of it is going to go up. So 537, we'll go to 538. Very simple rounding. This one, digit we're getting rid of is a 3. That's less than 5. So the preceding digit is unchanged, and that's 241. The question often comes up, what do you do if it's exactly 5? If it's exactly 5, I mean exactly 5, then you're going to round the number so it's even. That's a simple rule. You're going to round it so it's even. So let's say we have 17.75. Our 5 is our problem. Going to get rid of it. If we just got rid of the 5, it would be a 7, wouldn't it? That's not an even number. So, we're going to round this to 17.8. This is 6.5. Again, our 5 is going to go. We want our number to be even. 6 is an even number, so 17.6. So these are the two rules that are very obvious, everyone knows. The thing about rounding even is something that most people don't quite remember, but just remember, round it so it's an even number, but only if it ends in exactly 5. Any questions on that?
Wait, so why can't it be 17.7? That one.
This one?
No, the other one.
This one?
Yeah.
Well, because you're going to round this down. If this was a 7 here, that would be an odd number. Always shoot for even. Now, we also, as we were doing our measurements, we didn't talk about it in class, but the book talks a lot about accuracy of your measurement, precision, and stuff like that. I want to take a second and just distinguish between the two. Accuracy. Accuracy is a measure of how well your measurement correlates with some known value. So we know the density of water is some value. You measure it, it comes out that value, that's accurate. If you repeat it many times and you get the same value, you're being very accurate in your measurement. Precision indicates how reproducible it is. So if we have measured this many times, always get the same number, our number is also very precise. Now I think the easiest way to show this is with a dartboard. So let's go. All right. We're shooting for the center. If they hit the center, that would be very accurate. They're not in the center, are they? So this is not accurate. Nor is it precise, because we have measurements or darts all over the board. This measurement is neither precise nor accurate. All right, here we have 4 darts, nicely grouped together. That's very precise. However, we missed the center, so it's not accurate. And of course, finally, we have 4 darts in the center. This is a very accurate toss, and it's also very precise because they're all the same. We can show this in terms of a series of measurements using a simple graph. Let's say we're doing density. We know that density is mass divided by volume. Now in lab, we did water. In this little problem here, we say we have 25 cubic centimeters. The mass is 24.9 grams. What's the density? Well, we calculate that by mass divided by volume. Here our mass is 29.5, our volume is 25, and this gives us a measurement of 0.996. If you look it up, at 25 degrees, density of water is 0.996. So this is a very accurate determination. This is what you should have got in lab. Example, let's say we did this 4 times. We got roughly 25 or so each time for our mass. We would say that this is a very reproducible determination, so it is very precise, and they're grouped nicely around where the answer should be, right around 25-ish. So this is both accurate and precise. These are 4 measurements that are highly precise, but they're nowhere near where they're supposed to be. So this is highly precise, but low accuracy. Now here we take a bunch of measurements, and just by luck, the average of these turns out to be 25. That's just by luck. It is not an accurate determination, nor is it precise. They're scattered all over the place. And finally, here we have low precision and low accuracy. We're all up and down. We're everywhere. This is a bad set of measurements. Any questions? Now, density is something that you're going to be calculating on exams and quizzes. So I'm going to take a second and just make sure we all know how to do this. Again, it's mass per unit volume. Typically, we'll use cubic centimeters. You don't have to. It can be any unit of volume you want. Centimeters cubed is typical though. If we had a lump of gold, we've seen this one before, and this is 1 cubic centimeter, so 1 centimeter on a side, and we find it weighs 19.3. Mass divided by volume, volume would be 1, mass is 19.3. Our density would be 19.3 grams per cubic centimeter. Now in lab, we used a lump of metal that looks like this. It was about 1.2 this way, 1.2 that way, and depending on which one you had, it was either 5 or 5.4 lengthwise. Step 1, we need to find the volume of this. Now it's a rectangular solid, so the volume is simply going to be length, width, and height. Multiply them all together. 5.4 times 1.2 times 1.2. Calculator will tell you this is 7.776. Now, that's 4 digits, right? But think about this logically. Each of these measurements is only 2 significant figures, isn't it? How can we have an answer with 4 significant figures? Well, we really can't. What you have to do is look at your calculation, find the number that has the fewest number of significant figures, the fewest number, and then round your answer to that number. So we have to round this to 2 significant figures. Here we're rounding a 7. That means it's going to go up by 1. The preceding digit will, and this is 7.8. 2 significant figures because all of these guys are only 2. If this was 3, that was 3, and this was 2, you would still round only to 2. So, this is our volume, 7.8 cubic centimeters. Now we have a mass of 73, and our volume was 7.8. We do our division, and again the calculator spits out a number like this. How would we round this? How many figures? We have 3 up top, 2 in the bottom. We can only do 2. The fewest number of significant figures. So we have to round this guy to 2. There's a 5, but it's not exactly 5, is it? It goes up. So all of this is more than 0.5. Therefore, this rounds to 9.4. Any questions?
So it'll always go to whatever number that is after the point? It will never be like.
Well, it depends again on
9.3.
how many significant figures you're dealing with. If we had 3 significant figures here, we would keep the 5. So we're going to get rid of this 8. That would make that a 6. So you look and see how many figures you want. We want 2, so we're going to split here. And then ask if what's left here is more or less than 5. It's more, so this goes up. Now, one point I want to make here. When we talk about properties, we can describe properties that are intensive and extensive. Not really necessary that you remember the names, but an intensive property is something that is descriptive of the substance itself and is not dependent upon the mass. It doesn't matter how much you have, the intensive property will always be the same. Well, density is an intensive property. It's independent of the size of the sample. And I'm going to show that by doing this same calculation. Instead of 1 bar, let's say our sample size was 2 bars. All right? So our mass is going to be double, 146. Each of these has a volume of 7.8. So let's do our calculation. Density is going to be our total mass, that's 146, both bars. Our volume is 2 times 7.8. Multiply that out, do our division. The density is 9.4, just like before. Doesn't matter about the sample size. Density is an intrinsic property and will always be the same. Any questions? All right, we did one more experiment there. We took our little graduated cylinder and we added a stopper. Now, you weighed the stopper and you got some mass. I don't care what it was, you got a mass. We read our volume to start with at our meniscus. We dropped the stopper ring. Volume went up and we read it again. The change in volume represents the volume of our stopper. So, we know a mass, we know our volume, that's the difference here. So we can calculate the density. We know how much water it displaced, that means we know its volume. Density, quite simple. Again, mass divided by volume. Our mass is 43. Difference in our initial and final volume is this, 23.1 mils. Remember, 1 milliliter is the same as 1 cubic centimeter. They're the same. Always remember that. So simply do our division, and our density was 1.86 grams per mil, which is the same as 1.86 grams per cubic centimeter. Any questions? All right, just make sure you understand the concept of density. Make sure you go to Density 1, the tutorial, and work those. Because the problems that you see on the exam and on quizzes will look just like the ones on Density 1. The lab report for the first lab is online. It consists of a bunch of questions and then some density problems. Again, these are exactly like the problems, in fact, they're taken precisely from Density 1. So you can do this lab as many times as you want to earn your 10 points. Do try to have it done by next Monday. All right, let's go ahead and move into Chapter 2.
I got a question now.
Okay.
Okay, for the measurements that we did on Monday, well, we had an even number of 8 point for the volume of our water in a 10 milliliter. So really it should have been like 7.8 would have been a more accurate number because of the meniscus, correct? Okay. I just wanted to make
Yes, you
sure.
always want to measure everything, just like we did on the first slide.
Right.
Measure as closely as you can, get the digits that you're sure of, and then guess on the last one. That's how you do a measure. All right, let's review a little bit from Chapter 1 about atomic structure. Once again, here's my little classic atomic thing from the 50s. This is what we were all brought up thinking an atom looked like. Nucleus in the middle, electrons and little orbits going around it. We realize that this is not correct. That in fact, quantum mechanics says that these electrons exist as a cloud, and they exist in regions around the nucleus where everyone is a quantized energy level. We'll talk more about that in Chapter 3. This is a version of a simple atom. This is helium. We have 2 protons, 2 neutrons in our nucleus, and we have a cloud of electrons surrounding it. We know that this nucleus is very, very small. Atoms themselves, we know, are very, very small. We said in a single copper penny, there would be roughly 28 sextillion atoms. Huge number. The mass of a proton in the nucleus is 1.6 times 10 to the minus 24 grams. So a really, really tiny number. Remember, this is scientific notation. In order to get our 10 to the minus 24, we said we start here, move our decimal point until it's between our first 2 non-zeros, and that turns out to be 24 places. We're going this way, so it's a negative number. All right, a neutron is very similar to a proton, very similar mass, and an electron is much, much less. Now, this tells you something about the mass of an atom. The mass of an atom is essentially 100% in the nucleus. So let's look at our little atom here. I tried to draw this to scale, but I can't. As I drew this, I used a single pixel for my nucleus. But that's way too big. Way too big. Think about it this way. This is Wrigley Field, and that's a golf ball. If the nucleus was the size of a golf ball, and Wrigley Field was the electron cloud, that would be our nucleus, and this would be all of our electron cloud around it. So the mass is totally concentrated in this little tiny speck in the middle. So atoms are essentially empty space. All the mass in the nucleus in the middle. Now, we said that if we had an atom, a substance that composed of only one type of atom, that we would call that an element. Element, once again, only has one type of atom. Every element is identified by its chemical symbol. We pointed out that some of them are obvious, many of them aren't. Helium is He, that's pretty obvious. Iron, however, is Fe, that's for ferrium, not Ir for iron. So there are a lot. We also pointed out that we're going to organize these in something called the periodic table. Now, the periodic table we looked at was something like this. And again, these kind of make sense. H for hydrogen, Be beryllium, Mg magnesium, C for carbon, He for helium. Ne is neon, argon, krypton, fluorine, chlorine, bromine, iodine. O for oxygen. But there are some ringers in here. Ag is silver, Au is gold, Pb is lead, Sn is tin, Sb is antimony. Here's iron. Common ones. Na is sodium, K is potassium. Those guys you just pretty much have to learn. Now, the periodic table itself kind of looks funny. We'll talk about why it looks funny. But let's just do a little bit of history about where the whole concept came from. It was actually amazing. Historically, it was based on the fact that substances tended to react in a similar way but different. So there were a group of metals, solid metals, that were found to react with oxygen to give oxides, so metal plus oxygen. And they had the formula of 2 metals for every oxygen. A guy by the name of, let's don't do that thing yet. So this is a general observation. There was also a periodicity to the reactivity. That is, as we changed the metal, we saw a change in reactivity. Now let's just look at a cute example here. This is lithium metal, sodium metal, and potassium metal. You look at your periodic table, they're over here, lithium, sodium, potassium, right underneath each other. If you put a little bit of lithium in water, see it fizz? It just kind of fizzes and eventually goes away. Let's do the same thing with sodium. Now this is under oil to keep it away from the air. You'll note that the reaction here is much more vigorous. It's generated enough heat that the sodium is melted into a little ball, and it's skimming around the surface until it finally disappears. Now potassium is down here under sodium. When we do the same thing here with potassium, take our little chunk out, plop it in the water. It not only melts, but is so reactive that it actually causes a flame. The flame is because hydrogen gas is being evolved, and hydrogen is reacting with the oxygen, and that gives us the flame. So there's a tremendous increase in reactivity as we go down this particular little group of elements. This was observed by a Russian chemist named Mendeleev, and in 1872 he put together the first periodic table. The ones we just looked at here were lithium, sodium, and potassium, and all of these form oxides with 2 metals and 1 oxygen. Based on this type of logic, he put together this whole table, which is actually quite amazing. He misspelled table, but aside from that, it's really quite an accomplishment. Today's periodic table looks like this. There are 18 groups across, 7 down, 7 periods down, we'll call them. Though there's a little squiggly line here, we'll talk about what that means. And the general shape of the table. In chapter 3, we will understand exactly why all these things seem to be missing from this region. Like I said, going across the top, we have what are called groups. Now, there are actually 18 groups, but we're going to only be concerned with 1 through 8. So we're going to skip these guys in the middle. These are called transition metals. We'll do that again in a few minutes. The reason that we skip these is that the properties of these elements are transitional between those in group 2 and those in group 3. The groups we really want to deal with in this course are 1, 2, 3 through 8. Periods go down 1 through 7. Now, these are always written down here on the bottom. They actually squeeze in here, and we'll see why in a minute. Any questions? Well, let's just start off by using our periods and our groups as a grid and identify portions. What if I tell you we have an atom in group 1, period 4? Well, we would look at group 1, that's here. Go down period 4, we're dealing with K. What is K? Potassium. Stands for kalium, but K is potassium. So our element, group 1, period 4, is potassium. Do it again. Group 2, period 6. We're at 2. Go down to 6. We're at Ba. What do you think Ba might stand for? Ba is barium. One more. Group 8, period 4. Go all the way over here to 8. Go down to period 4, 1, 2, 3, 4. Kr. What is Kr? It's not kryptonite. It's krypton. Now we talked about a starter list of elements. I'm going to go through some sample questions off an old exam that deal with elements, their symbols, and their names. So let's look at this and give it a quick memorize. Mostly focus on the ones that don't you know, fit, obviously. Sodium, these guys pretty much all make sense. Phosphorus is a P, argon, potassium, make sure you know that. It's calcium, iron is Fe, that's copper. Zinc, bromine is Br, silver is an Ag, gold Au, and lead is Pb. So take just a minute, browse that over, and then let's just look at some of the questions that have been on old exams. All right, that's your 30 seconds. I assume you have it committed to memory by now. So let's just look at the type of questions that you might expect. Here we have a question, the symbols for silicon, arsenic, bromine, barium, and cobalt. What would those be? Well, we remember silicon. Silicon's a nice easy one, isn't it? Si. So right away we can narrow it down to these three. Bromine is Br, but all these have Br in it. Barium, we did barium, didn't we? What was barium? B8. So that's a good one. We have two BAs, so we're down to either B or C. AS, well, AS must be arsenic because it's the same. Cobalt, Cl or CO? CO. And that's our answer. Any questions? Which of the following elements has a symbol with two letters?
Silver.
We saw that fluorine was an F, right? Phosphorus was a P. Oxygen, sitting over there as an O. Silver, what was silver? Ag. Nitrogen, of course, is N. Silver, remember, is Ag. Gold is Au. What's in A? You'll never forget that one. Na is our friend, sodium. All right, here's another one with a bunch. Copper, chlorine, cobalt, carbon, and cadmium. Carbon we know is a C, so we can rule out E. Copper, what was copper? Cu. Cobalt is Co. So, let's see, we're chlorine is Cl, right? Not Cr. Therefore, that is our answer. This guy, which has only one letter. Iron is Fe, antimony is Sb, tin is Sn, sodium is Na, phosphorus is P. Phosphorus is P, not potassium. Remember that. And our last one here. Potassium is what? It's a K. Any questions? Well, let's think again about our periodic table. The elements in a periodic table are arranged numerically by what's called their atomic number. The atomic number, if you look at the periodic table here, it's the little thing up top. So 1, 2, 3, 4, 5, 6, blah, blah, blah. It's the number on top. What does it mean? The atomic number is quite simply, and this is important, remember this guy. The atomic number is simply the number of protons in the nucleus. The number of protons defines what the atom is. Doesn't matter how many neutrons it has, doesn't matter how many electrons it has. Anything that has 6 protons is going to be a carbon. The number of protons defines what element it is. And again, that's called the atomic number. Any questions? Very important concept. We can write what's called an atomic symbol. The atomic symbol is going to be the symbol for the element. So C for carbon. And it's going to have what's called a mass number and the atomic number. They're going to be arranged this way. We start off with what our element symbol is. Next, as a subscript in front of the element, well, okay, I did it backwards. Next, as a superscript in front of our element, we're going to put the mass number. Now, what's the mass number? Remember we said that virtually all of the mass of an atom was in the nucleus, right? So what's in the nucleus? Protons and neutrons. So mass number is simply the sum of protons and neutrons. Finally, as a subscript in front, we stick the atomic number. That is the atomic symbol for an element. Let's go ahead and just do some quick problems here. Go ahead and write an atomic symbol for hydrogen. I will tell you hydrogen has 1 proton, that's its atomic number, and it has no neutrons. So our symbol is going to be H. Our mass number is simply the sum of protons and neutrons. That's 1. And the atomic number, that's the number of protons, is also 1. So we would write it this way. Go ahead and do lithium. Lithium is here. It has an atomic number of 3, and it has 4 neutrons. The symbol for lithium, right over here, is Li. We would write our symbol, Li. Our mass number goes up top. That's the sum of 3 plus 4, and that is 7. The atomic number goes as a subscript. That's the number of protons. That's 3. So we would write lithium, mass of 7, atomic number of 3. To helium. Helium is 2 protons, 2 neutrons. Symbol is He. There's a post between me and helium. But there's helium right there. Our symbol is He. 2 plus 2 is 4. So that's our mass number. 2 protons in the nucleus, and we write it this way. Beryllium is a 4 and a 5. Our symbol over here is Be. 4 plus 5 is what? It's a 9. We have 4 as our atomic number. Beryllium, mass number of 9, 4 protons. Go ahead and do these, and I'll hush for 30 seconds or so. Let you just jot them down. Our symbols, in case you don't remember, oxygen is O, potassium is P, carbon is C, and iodine is I. Okay, that's our 30 seconds. Oxygen, 8 plus 8 is 16. Our symbol is O. We put 16 as our superscript. Atomic number is 8, and it looks like that. Potassium here, 19 plus 20. That's potassium, right? That's a K. I think I said P before. I did. I'm sorry. Sometimes you stand too close to the board here. So potassium, K is our symbol. We have 19 plus 20. What is that? That's 39, right? And we have a 19 as our atomic number. And that's our symbol. Carbon. 6 and 6 are 12. C is our symbol. 6 is our atomic number. And finally, iodine. Now I need a calculator to do this.
127.
And 127? Oh, okay. So 5374 is 127. I is our symbol. 53 is our atomic number. And it looks like that. Now this has appeared in many different forms on exams over the years. Let's look at one particular format. Mass number of argon is 40. Argon's here. It's also here. This element is in what period? Now remember, which are periods, which are groups. Groups go across, don't they? Periods go up and down. So we're dealing here with argon. So it's period 1, 2, 3. Likewise, it's in group 8. Now, how many protons in the nucleus? Well, what's our atomic number? Here it is. You look at it. Our atomic number is 18. Now, how many neutrons? Have to do higher math here. If our mass number is 40 and 18 of those are protons, how many neutrons? Must be 22. 18 plus 22 is 40. All right, go ahead and quickly write the atomic symbol. Again, this is Ar. Our mass number is going to be 40. Our atomic number is going to be 18. And it should look like that. Any questions? Neutral element, this is important, has 12 electrons and a mass number of 24. What's its period, what's its group, how many neutrons, and what's the symbol? Well, remember in an atom, protons are positive, aren't they? Electrons are negative. If the atom is neutral, there must be the same number of protons and electrons. So this is neutral, and it has 12 electrons. How many protons? 12. We're down here at magnesium. Go ahead and fill in the rest of the blanks here. All right, here we are. We are in what period? 1, 2, 3. What group? Group 2. If our mass number is 24, and we have 12 of those as protons, how many neutrons? 12. So our symbol is going to be Mg, mass number of 24, atomic number of 12, and it looks like that. Now, in addition to problems like this, you'll also see problems based on the tutorial from Chemistry Online called, I don't see it. It's called Protons, Electrons, and Neutrons. So let's look at it. This is a table. You're given a symbol. Here we're given a charge and the number of neutrons. What you have to do is fill in the 3 missing boxes. So let's look at our periodic table. Sn, what is Sn? Down here, Sn is 10. Step 1, what's its atomic number? Right there. It's 50, isn't it? So we're going to have 50 protons. 50 protons. If we have 66 neutrons, our mass number is just going to be what? 50 plus 66. Now our charge is +1. Note on the tutorial, don't put the plus in, just put a 1 if you're asked. But it's +1. Now in order to be +1, that means it must have one more proton than it does electrons, right? Because protons are positive, electrons are negative, we must have one extra proton. So if we have 50 protons, we must have 49 electrons. So what we just said is this. Atomic number is 50, 50 protons. The mass number, protons plus neutrons, 116. We have one more proton than we do electrons, therefore we must have 49. Let's do another one. Bromine here. Now I'm saying that bromine has a charge of -1 and we have 44 neutrons. Okay? Here's our periodic table. Step 1, we have to find bromine, don't we? Bromine is there. Or here. So you look for the atomic number. That's the number of protons. What's the atomic number? 35. Go ahead and figure out the rest of these, and I'll hush for a second. If we have 35 protons, our mass number is just going to be 44 plus 35. Now our charge is -1. That means we have one more extra electron, right? So we'll have one more electron than we do protons. Our logic is this. 35, therefore we have 35 protons. Mass number is simply 35 plus 44. We have one extra electron. Start with 35, add one more. 36 electrons.
I have a question.
Yeah.
So when it's -1 for the 35, then it's gonna be added 1?
We have one extra electron. In order for it to be negative, we have to have one more electron than we do protons. Do uranium. Now, if we look at our standard table here, it's not there, is it? That's because uranium lives down here at the bottom. We'll see why in a little bit. But uranium is down here, right there, at 92. Go ahead and fill in your table. Oops. Don't look at that. If the atomic number is 92, it will have 92 protons. The mass number is 235. So 92 of those are protons. That means that 230 or 143 must be neutrons. We are given that we have 92 electrons, we have 92 protons. What's our charge? 0. Same number of both, same number of positives and negatives. We're at 0. Now do practice this tutorial. You not only get your 5 points, but this is a format that you will see on your quizzes and on your exams. Yeah. You have to talk loud, I'm old. If you well, for the concept to remember for electrons is that in order for it to be neutral, you must have the same number of both. So we have 92 pluses, we need 92 negatives, that makes it 0. If we have one extra, we had 93 electrons, it would be minus 1. We had 90 electrons, it would be plus 2. So just look at pluses and minuses and see what you get back.
So in any case, the electron is always given, right?
Yep, no, it's not always given.
How do you figure it out?
You can figure it out. All right. Remember just a little bit ago, and I hope you do, I said that the thing that defines what an atom is what? The number of protons, right? I said it didn't matter how many neutrons you have, how many electrons you have, just the number of protons. Well, this concept gives rise to this notion of isotopes. This drawing here represents carbon. We'll see in the next chapter that the electrons in carbon are actually in 2 energy levels. We have inner electrons and we have outer electrons. Don't need to worry about that now. Let's just talk about our nucleus. For a mass number of 12, since its atomic number is 6, that means we have 6 protons and 6 neutrons. If we took this and we added an extra neutron, here we have our symbol for carbon 12, mass number of 12, 6 of those are protons. If we add one more proton here, we would wind up with a carbon with a mass number of 13. It's still carbon because it still has 6 protons. With carbon, we can do this again. Add another neutron, and we get carbon with a mass number of 14. These are referred to as isotopes. Isotopes are the same number of protons in the nucleus, that's the same atomic number, but differing number of neutrons. For carbon, we have what we refer to as carbon-12. Carbon-12 is the common form. About 1% of carbon exists as carbon-13. That's one extra neutron. And 0.0001% of all carbon exists as carbon-14, 2 neutrons. We'll see later in chapter 11 that carbon-14 is radioactive. Well, if carbon exists as 3 isotopes, one that weighs 12, one that weighs 13, one that weighs 14, how do you ever weigh out an exact number of carbon atoms? You do that based on the average atomic mass. Now, we're not actually going to do this calculation on an exam, but this is how it's done. What you do is going to look at the natural abundance. That is, how much of carbon exists as a given isotope. For carbon-12, it's 98.89%. 1% is carbon-13, and a trace for 14. To calculate the average mass, we would take the fraction, that's this, divided by 100, here, times 12, that's the mass. The fraction times 13, we'll ignore 14. When you multiply these out and add them up, the average mass of carbon is 12.01. If you look at the periodic table, you'll see the mass shown here underneath the symbol, look at it over here, is 12.01. That's the average atomic mass based on the isotope distribution. On Earth, the isotope distribution is generally constant. In the far reaches of the galaxy, it's not. And that's how you can actually determine a lot about where a given rock comes from. Is it a meteor? Is it from Earth? Is it whatever? Average atomic mass, our atomic number, and our atomic symbol. Now, you might wonder how chemists manage to do this. Determine exactly how much carbon weighs 12, etc. You do it using something called mass spectroscopy. This is a mass spectrometer. It's a nice big fancy machine. What you do is basically take a sample and you ionize it. So now it's positive. You accelerate it down this little pathway, and it would just keep going straight, except you hit it with a magnet. There's a big magnet. The magnet will bend the beam because the beam is charged. The amount that it bends it depends upon how much it weighs. Heavier things aren't bent as much, lighter things are bent a lot. You take and you analyze these, and you can tell how much of this has a given mass. Just as an example, this is for boron. Boron 11. The mass determined from a mass spec here is 11.009305. And those are all significant figures. So it's an amazing sensitive thing, and that winds up to be 80% abundance. Boron 10, 10.01, or 19.8% abundance. That's how we do it. It's a very sophisticated technique, very accurate, etc. Any questions? All right. This periodic table is black and white with a little bit of red all over. Many periodic tables, however, are colored. The one that I show all the time looks something like this. They're colored for a reason. When we deal with compounds, compounds are going to be two or more atoms stuck together. We're going to classify these as either molecular or ionic, depending upon the nature of the atoms. Specifically, we want to know if the atom is a metal, or a non-metal, or a semi-metal. So, if your periodic table is colored, in this case, everything is blue, is a metal. Now you see that most of these are metals, aren't they? All these guys at the bottom, these guys here, hydrogen is an exception. The things that are shown in yellow are nonmetals. Now the differences are, metals conduct electricity. We know that. Metals you can smash out. They're malleable. Nonmetals do not conduct electricity. They're insulators. And you try to smash a block of carbon, it shatters. The yellows here are nonmetals. Hydrogen is also considered a nonmetal. These little green guys in the middle, well, they're the transition between metals and nonmetals, aren't they? What would we call these? We'll call them semimetals. Now this should make sense to you. You've heard of silicon as a semiconductor, haven't you? It conducts some electricity, not as much as aluminum, and certainly better than phosphorus. It's a semiconductor. Boron, germanium, it's a classic germanium diode. Tellurium, antimony. These guys are classic semiconductors. Now, when we talked about groups, I said we're only going to deal with groups from 1, 2, and 3 through 8. Going to ignore these in the middle. That's because these guys are called the representative elements. Now, this is a very old classification. It used to be thought that these guys, the representative ones, were what you would find in a living thing. Now, this is really wrong. Really wrong. Because lots and lots of these guys in the middle also occur in living things, very important enzymes in your body, etc. But these are, again, historical, the representative elements. We'll also see that we're only going to deal with these particular groups of elements like that because discussing their atomic structure, exactly how the electrons are arranged, is really pretty simple. When you're talking about these guys, it gets much more difficult. These guys in between, the representatives, like I said before, this is a transition between group 2 and group 3. And these are called transition metals. Now, why are these guys stuck at the bottom down here? Well, they're really stuck at the bottom just for convenience. They actually belong up here. This slips in here after lanthanum. This slips in after actinamide or actinium, right up there. If we did put this together, put them in like they're supposed to, the periodic table would look like this. These would be referred to as the inner transition elements. But if you look at this, this is a very inconvenient looking table. Way too long and skinny. It's difficult to work with. We don't mess with these elements often anyway, so just pull them out, stick them at the bottom. Let's just make sure where they go. They go right here. And they're just part of the transition group of elements. All right, groups that you should know. Here in group 8, these are called the noble gases or the inert gases. Inert gases are called inert gases because they don't undergo reaction, at least not easily. We can, in fact, make compounds with these things, we'll see that, but they do it very grudgingly. They are the least reactive of all of the elements. Over here in group 7, we have the halogens. Make sure you know what all, at least the top 4 halogens are. Fluorine, chlorine, bromine, iodine. Those are the common ones. They're very reactive. We will use these a lot throughout the semester. Just like these are reactive, these guys in group 1 are also very reactive. We saw lithium, sodium, and potassium react with water. The reactivity increased as we went down, didn't it? If you take cesium, which is way down here, and toss it into water, it explodes instantly. It is very, very reactive. So the reactivity goes down. These are called alkali metals. Next to them, we have a group that are typically called the alkaline earths. Beryllium, magnesium, calcium, strontium, barium, and this is radium. We all know radium is radioactive. Now, this is the common periodic table that we all see and know and love. But there are lots and lots of other periodic tables. This is an example. This is a real periodic table. It is heck to try to figure out anything on it, but this is one of the compact versions where everything is shown cyclic. And again, these guys would slip in somewhere. I can't even figure out where they slip in, but they slip in one of these spots. Again, very unusual, but there are lots and lots of different periodic tables. Any questions? All right, let's wind up chapter 2 here just by doing some simple problems. An atom of phosphorus has an atomic number of 15, a mass number of 32. How many neutrons are in this particular isotope? Once again, these are real questions off real exams. So,
Say 17.
right, remember, what is a mass number? Mass number is protons plus neutrons, right?
Yes.
Now, if the mass number is 32 and 15 of those are protons, 17 must be neutrons. See, you can do this. Yeah. Any questions? All right, here we have bromine 79. Which of these properly describes bromine 79? How many protons does it contain? 35. The atomic number is the subscript, right? So we're looking at A, B, or C, possibly E. But these guys are possible. Our mass number is 79. So how many neutrons do we have? Well, 35 of the 79 are protons. We must have how many? 44 neutrons. Now, how about electrons? How do we know what the charge on this thing is? Whenever you show a charge on an atom, you show it after the symbol as a superscript, and it will be plus or minus depending on what the charge is. If it's neutral, you don't show anything. You don't see anything up here, therefore it must have the same number of protons and electrons. 35 protons, 35 electrons.
Would the charge be 0?
The charge is 0. Any questions? All right. A lot of people ask me to see this again. These are the tutorials we have so far. Today we added protons, electrons, and neutrons to the list. Once again, 5 points for each of these that you finish. Remember, however, you can only do them once. Okay, you can only get credit for scientific notation one time. So even if you do it lots, don't send it to me every time. I just have to figure that out. But we have 1, 2, 3, 4, 5, 6. That's 30 points added to your first exam if you get all of these. Next chapter, we're going to add more. Any questions?
What are these two?
That are due before the first exam. The morning of or the evening of the first exam. Okay? All right. You guys have a good evening.
Thank you.